Okay. Okay. So let's get started, and then please check your attendance on Blackboard. So I will leave what we learned in the previous class first. So we learned how to design FSM, right? So we started with the raw FSM, right? Raw type FSM. So like any digital system, the digital system that is developed include the four components: input, output, functional specification, and timing specification, right? So actually, the first, in order to design, so in order to design FSM, so we first need to identify input and output. But it's common. It's common for any digital design. We firstly define input and output ports, right? And then for FSM design, we need to define state transition diagram, right? So FSM includes multiple states, and then the state can be changed based on the input signals. Okay, so based on the input signal conditions, the next state is determined, right? So and then if we determine the state transition diagram, then we can make the state transition table and then output table. So I mentioned that those tables are similar to truth table, right? So in the truth table, we define input values and then the output signals determined by input values, right? So it's the same. So when we figure out the state transition table and then output table, then we can just define input and then we can also define output. But when we define the state transition diagram, we just define the state, right? The S0 and S1 or something like that. But we need to represent these states using by. Okay, so actually, so in the first question, you need to figure out the types of the FSM. So we can figure out the types of FSM using output logic, right? Okay, so we can figure out the types of FSM using output logic, right? So if output logic, the output values are determined by input and current state, and this FSM is Mealy FSM, right? And then if output logic is determined, output values are just determined by in a current state, the current state, then this is Moore FSM, right? Also, in the second question, so I asked about the characteristics. The main characteristics of sequential logic is the latch and then D flip-flop. The latch is level sensitive, right? Because if the clock is 1, then output is transparent to the input. So input values are just reflected to output. And then D flip-flop is edgy sensitive, right? So on the rising edge of clock, the output is updated by input values. So this is the D flip-flop. So you need to distinguish these different characteristics of latch and flip-flop, right? So very simple. So, okay. So In the previous class, I so learned. So I taught. So we learned how to design the FSM using Moore FSM example. So as I mentioned, Moore FSM, the output values are just determined by current state. But in the Mealy FSM, the output is just determined by input and current state. So we can design FSM using a Moore type FSM or a Mealy type FSM. Okay, so this was the second example, like smiling snail. Okay, so but you can understand that. So this is the input stream. So it's a input bit data. So the bit input this is the input bit data, and then we need to detect 0, 1, the sequence 0, 1 from the input bit stream, right? So in this example, we need to detect 0, 1, this one, and 0, 1, and 0, 1. Okay. So firstly, we can think about the Mealy FSM. So I mentioned that in the Mealy FSM, the output. So we can just define the state transition diagram like this. So we can define states, and the states are changed by input values. So, but on the arc, on this arc, you can find the two values, like this is input, and then this is output, right? So you can find the slash here. So this is the input value, then this is the output value. So on the arc, so based on the input values, the states are also changed, and then when the input is given, then outputs are also reflected. So output values are determined. So this is the Mealy FSM. So in the previous class, so in order to design the required FSM using Mealy type FSM, then we can define two states, right? It is because, so we need to detect the 0, 1, okay? So if the 0 is detected, then we need to check if the next input is 1 or 0. If the next input is 1, then the output needs to be 1, okay? But if the next input is 0, then actually it goes to the same state, okay? Because the current value is 0. So we define the two states. So S0 state means that, even though any numbers are given, then the output cannot be 1, right? And then S1 means that if the next input is 1, then output can be 1. Okay. So this is the Mealy FSM. Okay. So we can define two states, and then based on the input, then we can also define state transitions. Also, we can define output. Okay. So if the current state is S1 and the input is 0, then it goes to its own state. But if the input value is 1, then output is 1. Okay. So this is Mealy FSM. Then how can you design Moore FSM? So in the Moore FSM, you can find that this is the output. The output is determined inside of the state circles. Okay, state node. Okay, it's a node. So actually, when we design Moore FSM, so we can define the output value 1, so this state. But in order to detect in order to generate the output value 1, then we need to detect 0 and 1. So this is the input stream. Okay, we need to detect input stream 0 and 1. So actually this arc, so state transition is determined by input, right? So actually based on this input, then if this input stream is 0 and 1, then output needs to be 1. Okay? So you can observe the difference between Bohr FSM and Mealy FSM. So in the Mealy FSM, the output is immediately determined by input and current state. So when we define a Mealy FSM, we just use two states, S0 and S1. So I explained the meaning of these two states. But in the Bohr FSM, the output is included in the states. So, okay? So you can just think like this. So in order to make output 1, then we need to detect the 0, 1, this transition. Okay? So input, the transition by input values. So in order to design this Bohr FSM, so we need to define 3 states. Okay? And then if the state is in the S2, then output is 1. So based on this state transition, then we can just, so if the initial state is S0, then if the input is 0, then we can say that, oh, if the next input is 1, then the output can be 1. Okay? So it goes to the S1 state. And if the input is 1, then it goes to the S2 state enough to make output 1, right? But otherwise, if the in the S1 state, if the input is 0, then it goes to its own state, right? Because if the next input is 1, then we can generate the output 1. Okay? So based on the state definition, then we can also define Bohr FSM. So you can just compare Bohr FSM and the Mealy FSM. Okay? It's different, right? The state transition diagram is also different. Okay, but the main difference is that this one. The output is here. And then in the Bohr FSM, output is here. Okay. Then, so this is the Bohr FSM state transition table. Okay. So this is the Bohr FSM, and then based on this state transition diagram, then we can define the next state. But as I explained in the previous class, the next state is determined by current state and input, right? So you can find the arc here. Okay. So and then the next state is determined by input and current state, right? And then also we can use this state encoding. So we can make the state transition table. Then we can define Boolean equations. Okay. Then so in the Bohr FSM, the output is determined by only current state. So if you see the output table, then you can find that the input of this output table just includes the current state. So we cannot observe any input. Okay. So we can also easily generate the Boolean equation based on this output table. Okay. But in the Mealy FSM, so it's a different. So Mealy FSM has the only 2 states. So we can use this 1-bit encoding. If the state bit is 0, then it represents the state 0. And then if the state bit is 1, then it represents state 1 as 1. Okay, we can just use the 1 bit for representing two different states, right? So, and then also, Mealy FSM, the next state is also determined by current state and input. Also, you can find another column here. This is the output column. So this is also difference from the Moore FSM. So if you see the state transition table, the Moore FSM just has includes the next state column, but the Mealy FSM, because the next state and output are just determined by current state and input values, then actually we can just merge it. Next state table and output table in Mealy FSM. So we can so based on this state transition diagram, we can define the values of next state and output value. So the current state is 0. Okay, so 0. Then if the input is 0, then what is the next state? The next state is S1. So S1 is 1. So this is 1. And then at the same time, we can also figure out the output value, right? So this arc represents this low, okay, right? So what is the output? Output value is 0. Then how about the 0, 1? This row represents this arc because the current state is 0. This is 0, and the input is 1. So input is here. So what is the next state? Next state is also S0, right? So this is 0, and then what is the output? Output is 0. It's 0. In the same way, so if the current state is 1 and then input is 0, so current state is S1 and then input is 0 here, then what is the next state? The next state is the same as 1. Okay, you can just, so this arc is mapped to this low, right? So this is 0, and then also output is 0. So 1, 1, then so this arc represents also this low. So next state is this is 1. Okay, this is 0. Okay, so next state is 0, and then what is the output? Output is 1. So we can make the state transition table and the output table of this Mealy FSM. And then, so based on this value, and then also input and current state values, then we can just define Boolean equation, right? So this is just truth table, right? So so the next state is the A bar, and then the output is the S0 and A. Okay. So so in the Moore FSM, so actually based on the Boolean equation of next state logic and then output logic, then we can make the Moore FSM like this. Okay. So in the Moore FSM example, you can find that actually in order to represent the 3 states, we require 2 bits, right? So that's why the Moore FSM in this example, a Moore FSM requires 2 flip-flop, right? So this is the current state, and then this is the Boolean equation of next state logic So we can, so this is the next state logic NSL, and then this is the output logic. Okay. So, so, so if we see the Mealy FSM, so Mealy FSM has also the state register, but this state register has only one bit input and one bit output. So as I mentioned, this Mealy FSM example includes only two different states. So we can just use one bit for representing two states. And then, so next state logic is the A bar. Okay, so you can find the inverter here. And then output equation is the S0 and A. So you can find the AND gate here. So this is the next state logic, and then this is the output logic. Okay. So as you can see, the output logic includes the A, so this is the input, and then S0, the current state. Okay. So this is the Mealy FSM design. So actually it's the same design. Mealy FSM is designed based on the smiling snail, so same specification. And then Bohr FSM is also designed based on the smiling snail, right? So actually, so same specification, same functional specification is given. And then we can just design Bohr FSM, or we can also design Mealy FSM. But even though the result satisfies the functional specification of smiling snail, timing can be different. So you can think like that. Oh, actually, so we design the FSM using the same functional specification, like smiling snail. So you can just detect the 0, 1, input stream 0, 1. So we can design this function using Bohr FSM and Mealy FSM. But you need to remember that timing specification. Timing of Bohr FSM and then Mealy FSM is different. Why? Why? So it is because in the Bohr FSM, the output is determined by only current state. Okay, and current state is updated on the rising edge of clock. Okay, so which means that output in a Bohr FSM, output is determined, output is updated on the rising edge of clock, right? But Mealy FSM, so output is just determined by input signal, input and current state. But the current state is, so output is immediately updated by input value. This is the difference. So this difference makes the timing difference between a Bohr FSM and a Mealy FSM. Okay, because you can just observe that if the output is Y is updated immediately. Okay, immediately by input values. So let's see the timing diagram. So timing of Bohr FSM and Mealy FSM. So this is the state, and then this is the output of Bohr machine, Bohr FSM, and then this is the state, and then this is the output of Mealy FSM. Now this is the input. Okay, you can find the clock signals here. So the input is 0. Okay, so in the normal state, because the reset is 0 here. Now in the normal state, the input is 0. So initially, based on the because of the reset, then initially the 2FSM, the states of 2FSM is S0, right? So in the reset, at the reset, the S more is also in the S0, and then Mealy is also in the S0. And then output becomes input becomes 0. Okay. So actually, so this state represents the current state, right? Current state. So it's a 0, then actually the next state is updated here, but the current state is updated on the rising edge of clock, right? So because the input is 0, then it goes to the S1, right? And then at the same time, output is 0. So if you see the Mealy FSM, then it also goes to the S1, right? But let's see this time. Okay. So in the Bohr FSM, so the state is in the S1 and the input becomes 1. Then what is the next state? Next state is S2, right? So, but this state transition, the current state is updated on the rising edge of a clock. So S2, the current state will be S2 on this rising edge of a clock, right? And then when the current state is in the S2, what is the output? Output is 1. Okay, so output becomes 1 on the rising edge of a clock. Okay, because in the Bohr FSM, the output is determined by only current state, and then current state is synchronized with the clock signal on the rising edge of a clock. So which means that the output is also synchronized with the clock signal. Okay. But if you see the Mealy FSM, the Mealy machine, so if the current state is S1, then input changes at this point, okay, at this time. Okay. So here, and then so you can find that output is immediately changed because the input is changed at this point. You can find that, oh, in the Mealy FSM, output becomes 1 at this time. Okay? So when the input is changed, then output is immediately changed in the Mealy FSM. Okay? So if you see this output waveform of the output value, then you can find that in the Bohr FSM, the output becomes 1 for this time. Okay? But in the Mealy FSM, the output becomes 1 for here and here.
So I'm not really understanding. So for the Mealy FSM, like if you are in the S0 state and you put in a 0, you should go to the first state.
Right.
But then on the timetable, if you put in a 1, you go to the first state. Shouldn't it go to the 0 state?
So 1, yeah, it goes to 0 state on the rising edge of the clock.
That's for the Bohr FSM.
Huh? No. The difference between the Bohr FSM and Mealy FSM is that the output is determined by current state only. So this is the Bohr FSM. And then if the output is determined by current state and input, this is Mealy FSM. But the state transition. So, the next state is the combinational logic of using the current state and input. This is the same for the Mealy and Moore. Okay, so current state is just updated on the rising edge of clock. So it is because, so if you see this Mealy FSM, you can find that this is the current state, right? And then this current state is the output of T flip-flop, and then synchronized by clock, right? More is the same. This is the current state. Current state is the output of T flip-flops, and then also synchronized with the clock signal.
Can you go back to the next?
Okay.
So like, what I'm confused about is if you put in a 0 for the Moore FSM,
Okay.
you go to the S1 state.
Right.
And if you put in a 0 for the Mealy FSM, you go to the S1 state.
Right.
Right. But then you said that the Mealy FSM goes immediately. Like if I change to a 1, the state changes.
No. The state is always changing on the rising edge of the clock. So the output of a Mealy FSM is changing immediately, and the current state is only updated on the rising edge of the clock. Okay, so
both change later.
no. In a Moore, so in the Moore FSM, the output is also synchronized with the clock signal, because so as you can see, the output is including this state, right? And then this current state is updated on the rising edge of the clock. So it's later, right? As you said. Okay.
So the blue line.
Oh, this line. Okay.
So for the S1 state, we don't think about the 1, we think about the 0. Because if we input a 1 in the Mealy FSM, it should go to the S0 state.
S0 state in the rising edge of the clock. So next state. So the next state logic is updated immediately. So that can be confused because actually in FSM, the state transition is performed on the rising edge of the clock only. It's synchronized with the clock signal, right? Because the current state is the output of T flip-flop, right? But output can be different by Moore and Mealy FSMs. So if we see this Moore FSM, we cannot find any input. Okay, so Moore FSM, the output is only determined by current state. Okay, and then the current state is only changed on the rising edge of the clock. Okay, so which means that the output is also updated on the rising edge of the clock. Okay, but if you see the Mealy, the Mealy is also the output is determined by this input, and then input is not synchronized with the clock signal. So output can be updated immediately. But state is just the states are the output of flip-flop. So it's a synchronized with the clock. It can be confusing, but you need to understand, right? So this is the state. State is just updated on the rising edge of the clock for Moore and Mealy FSMs. But output is different. In the Moore FSM, output value is also synchronized with the clock, but in the Mealy, because the output is determined by input signal, in the Mealy FSM, the output is not synchronized. Output is not synchronized with the clock signal. It's just the different point is that just output. Okay. So as you can see, the timing can be different between the Moore FSM and Mealy FSM. Okay, and then it will the so you can find that usually the timing of Mealy FSM is 1 clock faster, 1 clock earlier than the output of Moore FSM. Okay, so it is because output is immediately updated. Okay. Okay, so I hope you can understand the difference between Moore and Mealy because timing can be it can be confused. Okay. So it is because the function is the same, but the timing is just different. Okay, then let's see let's learn about the vector FSM. So we learned how to design the FSM. Okay, we can design FSM using state transition diagram. So based on the input and output values, we can just define state transition diagram. Okay, and after we can define state transition diagram, we can easily design Moore FSM or Mealy FSM. So based on some definition, right? But sometimes this state transition can be complex. Okay. So in the previous example, like some traffic light example, we can just define 4 different states, right? But sometimes we can define very complex state conditions. Okay. So this is the example. So modify the traffic light controller to have parade mode. Okay. So in order to it's some special mode for the traffic light, and then in order to design this FSM, so we can need the 2 more input signals like P and R. So if the P is 1, then the traffic light goes to the parade mode. Then this Bravo what is the Bravo? I don't remember. I think the Bravo is the vertical traffic. Maybe. Where is the okay? So this is the vertical traffic, the Bravo, and academic avenue is the horizontal traffic. Okay. Okay. So this is the special mode, and then it's a parade mode, and then Bravo, light state green. So the light signal, the traffic light values are not determined by traffic sensors. Okay, and then if the R is 1, then it leaves parade mode. Then it goes to the normal operation mode. So the input is increased. So we can define this FSM like this black box like so FSM received the 4 inputs like the existing traffic sensor signals and parade signal and then read signal. Okay, and then we need to generate the traffic light value. So if we design FSM for this unvectored FSM looks like this. It's so complex, right? So we can find many transitions as arcs based on the inputs. So because the input signals are increased, the number of input signals are increased, so we can find many different conditions, okay, based on the inputs. So If we generate the FSM, then this FSM includes the eight different states, and also we can find the many conditions. So it's just so complex. So and then the hardware is complex, then we also require the complex hardware logic, and then the cost can be increased. So so in this case, if the FSM is so complex, then we can divide this complex FSM into multiple sub FSMs. So this is the factored FSM. Okay, so this is the mode FSM, and the mode FSM just determines the mode, the polite mode, and then also normal mode based on the P and R input, and then also the right FSM also receive the output from the mode FSM. Okay, so if the M is 1, maybe it's the polite mode, and then if the M is 0, then it can be the normal mode. And then the light FSM receives the traffic sensor signal, and then mode signal from the mode FSM, and then it can generate the traffic light values. So we split this complex FSM. So it's a very complex FSM into the two FSMs, like mode FSM and then light FSM. Okay, so we can design FSM like this. So if you see the example, so factor the FSM visually. So the traffic light FSM includes the 4 states. So it's the same, right? It's the same to the previous example. So it only includes the 4 FSM. And then mode FSM includes the 2 states, like, right? So normal mode or polite mode. Okay. So you can find the M input here. So this is modified based compared to the previous example. But if we see this factor FSM, then we can understand. We can easily understand because it's not complex. It's a simpler. It's a simpler than the previous unfactored FSM. Okay, so we can design FSM so more easily. Okay. Okay, so we complete the FSM part of the textbook, and then please read the chapter 3.4, the textbook. Okay, then let's go to the next topic. The hardware description languages. So we learned about the sequential logic, and so we learned about the FSM, and now we need to learn how to design this sequential logic and FSM using system Verilog. Okay, so this is just a review. So we learned about the D-latch, and then D-latch is the D-latch is level sensitive. So if the clock is 1, then it's transparent. The output is transparent to input, and then if the clock is 0, then output holds the previous value. Okay. So as I mentioned, that we can design the latch like this. So we can use the array of the latch. Then this is the level sensitive. Okay, if the flag is 1, then Q becomes the input D. And then flip-flop is the edge sensitive. So we need to use the array of the FF in system Verilog. And then sensitivity list needs to include the rising edge. The rising edge clock. So we need to use the positive edge clock in the sensitivity list. This is the deep flip-flop. Then we learned about the different type of deep flip-flops, like enabled deep flip-flop, and then reset deep flip-flop. Okay, so this is the example of asynchronous reset. So if we use the asynchronous reset, Then the sensitivity list includes the condition for the asynchronous reset, like negative reset. Okay, and then we describe the output values based on the reset signal. Okay, that's what we learned. So now we will learn about the blocking and non-blocking assignment. So actually this is blocking and non-blocking. So this is the some unique characteristics of HDL. So unique. So it means that so it can be a little bit tricky. Okay? So because so this property, this blocking and non-blocking is different from the some normal programming language. Okay, so this is the unique uh, syntax of the HDL. Okay, let's see what's different. So this is the example from the combinational logic design. So we just learned about this combinational logic design. Okay, so we learned that we can just implement the combinational logic using always statement, right? And then if you see the inside of always statement, then you can find the multiple assignment using equal sign, right? Equal. Then some students notified this. But if you see the inside of always underbar FF, it's a flip-flop design, you can find this sign. So it looks like the arrow sign, right? With this sign and then equal sign. So it looks like the arrow. Okay. So you can think that why? So its meaning is very similar. Okay. So output becomes input, right? But I use different symbol. So for this combinational logic design, I use equal sign for assign, so signal assignment. But inside of the flip-flop, so in order to implement the flip-flop in system value, I use this sign, arrow sign, right? What is it? So actually, I believe you can easily understand the design, but it's a kind of the meaning is a little bit different. So I will explain. So this arrow sign is called the non-blocking assignment. So it's a non-blocking. So what's it mean? So you can understand that this arrow sign is the concurrent assignment. What's the concurrent? Concurrent means that it's the in parallel. Okay, so at the same time, the output is updated by input values in parallel. Okay, 병렬적으로 in parallel. So this is the meaning of non-blocking. So for example, A is B, and then C is D. So in this example, I use non-blocking assignment. Okay, so you can find that A becomes B and then C becomes D. But this assignment is performed in parallel. So that's why it's called the non-blocking. So if the order is changed, like the C equal D, and then A equal B, so you can find that the assignment orders is changed, right? So C is updated first, and then A is first updated first in the code, but actually it is updated in parallel. So actually, if we just check the timing, this is equivalent. Okay, so updated in parallel, concurrently. This is the meaning of non-blocking. And then this equal sign is the blocking assignment. So it means the order of the assignment is sequential. It is sequentially updated from top to bottom. So if we use the A equal B and then C equal D, so actually the output it can be same, but it represents the firstly A is updated by B, and then C is updated by D. So if the order is changed, like the C equal D and then A equal B, so if I use the blocking assignment, like equal sign, it means that C is firstly updated by D, and then A is updated by B. It's a sequentially. So we can find some sequence, the order in the blocking assignment, but if we use the non-blocking assignment, the all values, output values are updated concurrently in parallel. Okay, in parallel. This is different. So why is it required? It is because we are designing hardware. It's not software. We are designing hardware, and then if there are multiple blocks in the hardware, then also like deep flip-flop, on the right hand of the flip-flop, all values are updated in parallel, right? Right. So like the So if we see that this example, this is the output signal S0 and this is the output signal S1, but S1 and S0 are updated at the same time on the rising edge of the clock. But this update is concurrent. So it's a concurrent update. It's a parallel update. Okay. So because we are learning about sequential logic using deep flip-flop, then we require non-blocking assignment. So that's why inside of the flip-flop, so when the flip-flop is implemented, then we normally use non-blocking assignment. So I said normally, so that okay. So it can be tricky. Right? So I said it can be tricky. So it is because also this is some unique difference between the software and the hardware description language. So any programming language and then this hardware description language. Hardware description language support non-blocking assignment. Okay. So this is the example. So as I mentioned, so you can find the two D flip-flops here, and then D0 and then D1 is here, and then also these two D flip-flops are synchronized with the same clock signal. Okay, so and then the output is Q0 and Q1, and then we already learned that in the D flip-flop on the rising edge of the clock, the Q is updated, but this update is updates occur in parallel, right? Just simultaneously and or concurrently. Okay? So at the same time, the Q0 and Q1 is updated. So in this case, we need to use non-blocking assignment. So if the signals are updated simultaneously or concurrently, then we need to use non-blocking assignment. So this is the example of blocking assignment. It's a combinational logic, right? So this is the example of combinational logic. Oh, it's very similar to the exam question, right? So why this y is updated, but in order to determine the y, to determine the output value y, firstly, and we need to know the n3. So we need to know the n2, and then also we need to know the n1. So what does that mean? Because using this b, n1 is updated first, right? And then using this n1, n2 is updated. So like this, n1 equal not b, and 2 equal n1 and a. So in order to make the n2 signal, we firstly update the n1. And then in this example, I use the blocking statement. Why? It's not concurrent. So it's not concurrent. So firstly, n1 is updated. Then using this value, n2 is updated sequentially. Sequentially, one by one. So I use the blocking statement. So if you see this equal sign in then you can we can just understand like the actually normal programming language. Okay? In the programming languages, actually all values are updated immediately, right? So actually blocking statement, it means that it is updated from top to bottom sequentially. Okay. So and then actually in the combinational logic, we can observe that the signals are updated immediately, and then it's updated to the next logic or next logic. Okay, sequentially. So in the combinational logic design, we use blocking statement. So it's a different. So in the deeply block, all output Q0 and Q1 are updated at the same time in parallel, concurrently. So we use the non-blocking statement, and then the combination logic, the internal node is updated immediately. So the connected like this. So we need to use the blocking statement. Okay? Blocking assignment. So this is the example. So this always statement implement this combination logic that you can find that n1 is firstly updated, then n2, then n3, and y. Okay, and then I use blocking statement. Okay, so this is the meaning of blocking assignment. So this is the example. So blocking executed sequentially in order from top to bottom, and then non-blocking executed concurrently in parallel. Okay. So this is the same always on the FF, and then you can find that. So this is the sequential usually it will flip, and then so in the left side code I use the non-blocking statement. In the right side code, I use the blocking statement. So it's the same word different. Same word different. It's different. So why? Because in the right side code, so I use the N1. N1 is firstly updated immediately because it's a blocking statement. And then this value goes to here, and then there's an update to the queue. But in the left side code, I use the non-blocking statement, non-blocking assignment. So N1 and Q are updated in parallel. So if this logic is synthesized, it looks like this. It's different, right? So meaning is also different, right? Also synthesized result are also different. So this looks like this. So firstly, the N1 is updated by this flip-flop, and then 2 is also updated. And then, but if we see this one, then it is equivalent to the Q is updated by the 1 flip-flop. Okay.
If non-blocking assignment will be done, will be executed. One, the box appear if at the same time Q and N1 change statement, but because N1 is not assigned yet to E, doesn't the bug occur? Yes, like N1 isn't assigned at that time, and Q is assigned to N1. And at that time, wouldn't get the error.
Error? No, this is an error. So actually, so you can find the two flip-flops, the back-to-back flip-flops, right? So and then these flip-flops are synchronized with this clock signal. Okay. So based using this P, then N1. So this is N1. The N1 is updated, but on the rising edge of clock, right? But this update is just slightly delayed because the flip-flop has also exceeded the delay, right? But the clock is synchronized. So N1 is updated after some delay. So at the next clock, this N1 is updated to the Q. But this is not an error. So it actually the D is propagated to the N1 on the first rising edge of the clock. And then on the second rising edge of the clock, then N1 is updated to the Q.
So the difference between them is the time they will be executed.
The time is different. But this one, actually, only one flip-flop is synthesized, generated. Okay. So, any question?